Just chill out.
Calm down, Sticky.
I know.
How was your Thanksgiving?
Thanksgiving was good.
Did you hunt your turkey on the farm?
Did you hunt?
No.
What? Are you a hunter?
No, I've tried it. I'm a bird shy.
I've actually never shot a gun.
All right. So what we've got today is kind of random things that all kind of make sense at the end. So what I'm going to do is I'm going to go over actually to the big whiteboard over there, and I'm going to write down a whole bunch of stuff and derive an equation for what's known as a perfectly elastic collision. Do not write it down, okay? I'm only going to show you about half the process anyway. I will never expect you to derive this whole equation. When we get to the end, you'll see, oh, this is kind of what we end up with, okay? So don't flip out and go, oh my God, oh, we have to do this. No, it will literally, but it will take up like that entire board over there. So don't flip out, don't write it down, pay attention to what I'm doing, okay? But you don't have to derive this equation, okay? So, Kyle, just, okay, don't flip out on me.
I'm not going to write it down.
Okay, if you want to, you can, but I'm just saying. You know.
Reese, you guys can
All right.
I don't know where to put it.
With all that together,
Here. Okay, that's fine. I'm not in it right. No. Now you are. It's not. I'm gonna really good. I'll just scoot out this way. Okay. So you know you can. Can everybody see? Can you see? Okay.
Yeah. Oh.
That's supposed to be a G. I don't know what that is. He.
Well done.
And what's the thing?
Okay, so first off, you got to get straight in terminology. Basically, all collisions fall into one of two categories. It's either going to be a perfectly elastic collision, and you have to be told, this is a perfectly elastic collision. This is an absolute idealized situation where the momentum and the total mechanical energy are conserved. So you're not losing any energy to friction, to heat, to sound, to breaking glass in a car wreck, nothing. Okay? Whatever you start with in terms of the energy is whatever you end up with in terms of the energy. But you have to be specifically told this is a perfectly elastic collision. Now, realistically what happens is that you have what's known as an inelastic collision. With an inelastic collision, you will still conserve momentum. Momentum is always conserved. But we're going to lose energy, okay, in the sense that we won't have it in terms of kinetic energy. Like, for example, if there's a car crash, you're going to lose energy in the collision process. You're going to lose energy to friction. You're going to lose some of that energy to breaking the glass, okay, whatever it is. So this is like an idealized world. In reality, this is what takes place. So you would have to be told this. So now, what I'm going to start to do is I'm going to work through this perfectly elastic collision, and we're going to see what happens with the math. So again, don't write all of this down because it's going to take me a while. So typically what you have is a bullet and a target. So what you start off with is saying, okay, here's the kinetic energy of the bullet plus the kinetic energy of the target is going to equal the new kinetic energy of the bullet plus the new kinetic energy of the target. Okay, start with this. Whatever energy I have here has to be the same energy over here. So this is going to be 1/2 mass of the bullet, velocity of the bullet squared, plus 1/2 mass of the target, velocity of the target squared, equals 1/2 mass. This is why this becomes fairly tedious. It's 1/2 Okay. So here's the deal. So what can I do to make this a little bit simpler so I don't have to rewrite a whole bunch of things? Yeah, I can multiply both sides by 2. So that's going to make life simple. That way I drop out all of my halves and I don't have to rewrite those. So at this point, all of my 1/2s are gone. Life's cool. Okay. Now, what I want to do is I want to get all of the bullets on one side and all of the targets on the other side. So I'm going to get mass of the bullet, the original velocity of the bullet squared, minus the mass of the bullet times the original as new velocity of the bullet squared. Then I'm going to do the same thing with the targets. So I'm going to have the mass of the target, new velocity of the target squared, minus the mass of the target times the original velocity of the target squared. Okay. Now, at this point, what can I do to simplify this a little bit more? Do what?
Take out the masses.
Yeah, I can't cancel out all of the masses because the bullet and the target are going to be different. So I can't just cancel them out, but I can factor it out. So this is going to be the mass of the bullet times the velocity of the bullet squared minus pound squared equals the mass of the target. Okay. Now, so we need a quick break back into the days of your Algebra 1 adventures. And let's say that I gave you, I want you to factor x squared minus 9. Mr. Rollins. Mr. Rollins, you have x squared minus 9. You have the difference of 2 squares. How do you factor the difference of 2 squares?
It's going to be x plus 3x minus 3.
What'd you say?
X plus 3x minus 3.
Beautiful. Now, is this the difference of 2 squares? That's squared and that's squared, right?
Yeah. I'd say it's different.
So this is the difference of 2 squares, true? So I can rewrite this as the mass of the bullet times the velocity of the bullet plus the new velocity of the bullet times the velocity of the bullet minus the new velocity of the bullet. True? Because this is the difference of 2 squares. So all I did here was the same thing that Mr. Rollins did down here. Okay? X plus 3, x minus 3. Velocity of the bullet plus new velocity of the bullet, boom, boom, same deal, right? Mr. Rollins, can I do the same thing over here?
Yes.
Okay? So this is going to be the new velocity of the target minus the velocity of the target, new velocity of the target, plus the velocity of the target. Okay. Go with this. Okay. Now, at this point, I'm going to just leave this for now. I'll get back to it. Okay? We'll get back to this point. So now, we also have to conserve momentum. Kendra, how does any conservation of momentum problem start?
The momentum plus the original momentum plus the other momentum equals the momentum prime plus momentum prime.
Beautiful. So in this case, this is going to be, I'm going to have 2 things. Okay? So imagine here's a bullet traveling towards the target, right? The bullet target. So this would be mass of the bullet times the velocity of the bullet plus the mass of the target times the velocity of the target is going to equal the mass of the bullet times the new velocity of the bullet plus the mass of the target times the new velocity of the target. True? Conservation of momentum. Straight up deal. Boom. Nothing fancy. So I can do the same thing here as I did here. I'm going to move all my bullets to one side. I'm going to move all my targets to the other side. Okay? So I'm going to write this as the mass of the bullet, velocity of the bullet, minus the mass of the bullet times v prime of the bullet is going to equal the mass of the target, v prime of the target, minus the mass of the target, velocity of the target. Now, what can I do here? Factor out A, right? So I get mass. Okay. Now, because of the fact that both of these things have to be equalities at the same time, basically I'm going to divide both sides by this. Okay? I'm going to divide both sides by this whole thing here. So I'm going to take this whole thing, and then I'm going to divide it by the mass of the bullet times the velocity of the bullet minus v prime of the bullet. And that's going to equal the mass of the target times v prime of the target minus So now what happened?
You lost me.
No, both sides are equal. So all I did was I divided both sides by this quantity.
Yeah.
Okay? So now what's going to happen over here?
Do the masses cancel out?
Well, I can lose the mass of the bullet, right?
And one of those binomial things.
And then I can lose one of these. So I get the velocity of the bullet plus v prime of the bullet. And then I can lose these, and I can lose this. And then get v prime of the target plus velocity of the target. So this is kind of like a little self-check that we'll look at once we get into this. So if this is true, if I add the velocity of the bullets together before and after, that should equal the velocity of the targets before and after the collision. Okay? Now, a lot of the times, your velocity of your target is going to be zero, the initial velocity, because the target's just going to be sitting there. So these might, this obviously can't be zero. If the bullet's going to hit the target, it has to be moving. So this one cannot be zero. You'll see, because this one cannot be zero, and if the target starts at rest, that means afterwards the target has to be moving. Okay? This has to be moving. So the target might start at rest, but afterwards it has to be moving. The bullet might end up at rest, and you'll see how that's going to work out, but it has to be moving. So what this means is that both sides of this equation can't be equal to zero. Because if they are, then it's like, well, nothing's happening. Because the target's at rest and the bullet's at rest. Well, that's cool to watch. Okay, so as long as this is moving, here's what's going to be important. That means after the collision, the target has to be moving. So the target cannot be at rest after the collision. Now, if you go through a whole nother set of mumbo jumbo and putting this back in here, which would take me another half of a page, here's where you're going to end up. I just wanted you to see how this deal is going to play out. This is why I said, on your final, I'm not going to say, here's a blank piece of paper, prove that in a perfectly elastic collision, both momentum and energy are conserved. I'm never going to make you do this. I just wanted you to see where this whole thing comes from. So, at the end of the day, here's where you end up. This is what I'm going to expect you to know how to use.
It wasn't that bad, you just wrote really big.
Well, yeah. Okay. So this is the heart and soul of what you got to be able to use. So let's talk about this. So let's talk about the new velocity of the bullet. So is it possible for the new velocity of the bullet to be zero?
Yes, if it gets stuck.
Yes, why, Hunter?
You know, I was just thinking the bullet hits a target, it's gonna stop, so
Possibility,
that's what I was thinking.
and that's a good thought.
That is my reason.
But mathematically, how can this thing go to 0?
MB minus
I don't know what
MB
the
equal MB plus MB.
No, you're making this difficult.
Uh,
Yeah, it's math, the target and the bullet are the same mass, okay? If these two values are the same, if they're both 1 kilogram, 0.1 kilogram doesn't make any difference. If the bullet and the target have the same mass, you subtract those out, this becomes a 0 value, which means if that's the case, if the bullet hitting the target, a perfectly elastic collision, if this thing stops, that just means the bullet comes to rest. Okay? We're doing it. Stops. Now, is it possible for the new velocity of the bullet to be a positive value?
Yeah.
Ms. Treadway, what would have to happen for the new velocity of the bullet, assuming that the original velocity was positive as well?
I think the mass of the bullet have to be greater than the mass of the target.
Yeah. So if you've got a really big bullet hitting a smaller target, that means after the collision, the bullet's going to keep going in the same direction that it was, and the target's going to take off. Okay? So it's possible for this to be positive. So in other words, the bullet hits it, and then it keeps going in that same direction. Is it possible for the new velocity of the bullet to be negative?
Yeah.
Yeah? How?
Bounces back like off rubber.
Yeah, okay, but mathematically what has to happen? You're right, but what has to happen mathematically?
The target has to weigh more than the bullet.
Yeah, if the bullet has less mass than the target, then when I subtract it, this becomes a negative number, right? And then that can work out. Now, is it possible, and this goes back to this idea here with this equation, is it possible for the new velocity of the target to be 0?
No.
No, because look, you're not subtracting anything over here.
You just said
Okay? So basically when I take mass of the bullet times the velocity of the bullet, what am I finding here? Momentum. So this is basically 2 times the momentum of the bullet, right? So as long as this is a non-zero value, my velocity of the target has to be a non-zero value. Now, is it mathematically possible for this new velocity of the target, assuming that this velocity is positive, is it possible for this to be a negative value?
no.
Why?
Mass doesn't have a negative.
Yeah, my masses aren't going to be negative because this is the sum of them. This is going to be a positive value. So what this means is that after the collision, the target has to be going in the same direction that the bullet was. Okay, so that's what that means mathematically. Physically, what it means is this. Here's the target, and here comes the bullet, right? So the bullet's going to hit it. So what would it mean if you said, well, the new velocity of the target is negative? So what would that physically mean?
Not flying in your face.
Well, yeah, the bullet's going to hit the target, and then you're going to tell me afterwards the target's going to go in this direction, which would be cool, but yeah, it's not going to happen. There's no way that it could happen. Okay, so let's see if all of this works as some mumbo jumbo. So we're going to work through a simple example. Now, this is a very idealized situation. And typically this always plays out typically with collisions involving like subatomic particles like protons or helium nuclei colliding with other helium nuclei in a vacuum, because you don't have to worry about any interference. But we're going to work through just a simple example and see if it works. So let's say that I've got a 3 kilogram bullet, which is pretty big. And if we hit a 1 kilogram target, that's at rest. Okay? So, the bullet's coming along, and it's moving at 4 meters per second, otherwise it's not going to hit it. And it's going to collide with the target that's at rest, and then we want to see what's going to happen. So, let's start with this. Can I find the new velocity of the bullet?
Yes.
Yes. Okay? So the new velocity of the bullet is going to be the mass of the bullet, which is going to be 3 kilograms, minus 1 kilogram, times the original velocity of the bullet, which is 4 meters per second. And then I'm going to divide that by the sum of the masses, which is going to be 4 kilograms. So basically I lose my 4s. So I get 2 meters per second. So, did the bullet slow down after it hit the target? Yeah. Okay, it was moving, it hits the target, boom, slows down. Okay, which makes sense, right? The target can't, or the bullet can't speed up after the collision. Okay, so I got that number. Now, new velocity of the target. So, that's going to be 2 times the mass of the bullet, which is 3 kilograms, times velocity of the bullet, which is 4 meters per second, divided by 4 kilograms. 4's cancel out. I get 6 meters per second. Now, if all goes well, this little sub-step here should be valid. So if I come in here and say, okay, the original velocity of the bullet was 4 meters per second. Okay, so that's cool. And then the new velocity of the bullet was 2 meters per second. The original velocity of the target was 0. And the new velocity of the target is 6 meters per second. Okay? So this little sub-steps, okay, hey, we're good so far. This part's cool. All right? Okay. Now, let's look at and see if momentum is actually conserved. So, if you go back to what Kendra said, we need the original momentum of the bullet, which is going to be what, Kendra?
4 meters per second.
Times?
The mass, 3 kilograms.
Which gets you?
12.
12. So, the original momentum of the system is 12 newton seconds. As this was moving at 3 kilograms, moving at 4 meters per second. Cool with that. Okay, so we got that. Now, afterwards, this 3 kilogram mass is moving at 2 meters per second. So that gives me 6 newton seconds, right? And then my bullet with a mass of 1 kilogram is moving at 6 meters per second. So that gets me another 6 newton seconds. Check my math, but 6 plus 6 equals 12, and we're cool. Okay? Now, don't think that these always get split. It just happened to work out that way. Okay? So don't look at this and go, oh, the momentum. No. No. It just happens to work out that way. All right. So the momentum side is cool. What else has to be conserved?
Energy.
Energy. Okay, so I got a 3 kilogram mass moving at 4 meters per second. So I'm going to have 1/2 times 3 kilograms times 4 meters per second squared. So I get 16,824. So then I'm going to have that 3 kilogram mass moving at 2 meters per second. So that's going to be 1/2 3 kilograms times, what was it, 2? And then I'm going to have a 1 kilogram mass moving at 6 meters per second squared. So for 6 joules, 36, 18 joules. 6 plus 18, I get 27. Well, so I conserve both momentum and energy. That's perfect. Now, how this plays out. Come back here. Good? Okay. So let's say here's the target, and let's say here's the bullet. Same mass. So if this is a perfectly elastic collision, barring any external forces, it's perfectly flat, there's no friction, anything like that. So when this comes in and hits it, this is the same mass as this one. So what should happen to the target?
Target,
Target should,
go that way.
bullet should,
Stops.
because if you look at what's going to happen, if you look at the new velocity of the bullet, it's going to be the mass of the bullet minus the mass of the target. So if these two masses are exactly identical, and assuming that we don't lose any energy anywhere else, this one should stop, and this one should take off with the exact same energy and the exact same momentum. So, come in here, hits, okay, and got a little bit of roll. Masses might not be exactly the same, okay, but this one basically stops, this one takes off. So this takes all of its momentum, all of its energy, transfers it directly to this, there we go. Now, I'll make this one the target. So now I've got a very, very massive target and a relatively small bullet. So now what should happen?
Let's go that way.
Mr. Hunter,
Negative. It's gonna come back. It's gonna bounce.
what's going to bounce back?
The bullet. Or
Are you
the-
sure? Or the target?
Not the target. It can't.
Why not?
I mean, it could, but
Yeah, because that would be like, I'm gonna roll this thing in, it's going to hit, and then they're both going to go in this
well,
direction,
that can't happen.
which would be cool.
Right.
Yeah, but it's not going to happen.
Right.
So let's see what actually happens, all right?
Whoa. Whoa.
That just felt good.
I honestly.
You think it? Okay.
Yeah.
Did I lose any magic the second time through?
I just, that's one right there, like, it just gives me a warm feeling.
Okay, all right. Now I know what to tell Santa Claus to bring you for Christmas. Okay. Okay. So mathematically, when I take the mass of the target and subtract the mass, excuse me, the mass of the bullet and subtract the mass of the target, I'm going to get a negative number, right? So that means that's why this thing is going to hit and bounce back. So come in here, bink, okay? Now, if I make this the target, and I make this the bullet, excuse me, I make this the bullet, I make this the target. So now, what should happen?
Let's try it.
Both gonna go that way.
Yeah.
Okay, so I'm going to do this.
Oh, they're
Both
both
gonna
gonna go off
They're both gonna
together.
go that direction.
Together? Are they going to stick together?
No, no, no.
No,
That one's
no,
gonna
no.
stop.
Lighter
This
one's
one's
gonna
gonna
go faster.
This one's going to stop.
Yeah.
No, it's
It's
gonna
gonna
keep
keep
on
on
going.
Keep going.
Okay, so you're saying this one's going to keep going,
So many possibilities.
and this one should go.
Faster than that one.
Okay, let's see what happens.
Look at that.
Okay.
That's right.
Now,
That's just satisfying.
two continents. I've never heard anyone say, that's just satisfying.
They really do.
Okay.
Like,
Oh, I'm sorry.
All right, so look what happens to the distance between the two cards as they roll. So this goes in. So what's happening to the distance between them? It increases because the target is going faster than the
Bullet.
bullet is, okay? So it comes in, hits, boom, it is
Give
quite
me a
satisfying.
scenario where that.
When
Like,
you run into someone,
Yeah, or if you have like a smaller bumper car, you're getting hit by a much more massive bumper car. And again, this is a completely idealized situation. Yes,
so if you're in bumper cars and you're in a smaller bumper car, how do you win that exchange?
you don't. You run and hide.
you'd have to go faster. Velocity.
Test that out.
But like, if I,
Cars.
Can we go do that?
Okay. Now, what if I did this? So let's have another situation. Okay? Where got one at rest. Steady.
I wanna play bumper cars
Okay.
now.
Whoa. Yeah.
yeah, they're magnets.
Okay? So, could this situation be a perfectly elastic collision?
No. Have confidence in yourselves, guys.
Okay, say that again.
Okay, because this situation where one is at rest, this one comes in and hits it, and they move off together. Could this be a perfectly elastic collision? Well, look what happens mathematically, okay? First off, mathematically, the two velocities are going to be different, right? Okay? And with this one, they're not, because of the fact they're moving off together. So whenever two objects hit and move off together, it cannot be a perfectly elastic collision.
How does that work? Like,
Because you lose energy in the act of the collision. Okay? That's the biggest thing. That by making those two objects stick together, you usually lose about 50% of your mechanical energy that way. So if you go back and think through that ballistic pendulum problem that we did, where I pulled the spring back and I shot the ball into the pendulum and then it swung up, the reason that I couldn't take the energy that was in the ball and then say, okay, well that's going to be the energy at the top of the swing, is because they hit and they moved off together, I lost a lot of the energy in that collision. So, but here's what's still going to be true. You will always conserve momentum. So if you have a problem like this, okay, if you go with the Kinder equation, so here you have the mass of one, here's the mass. Now, if these are identical, if the two masses are identical, and let's say this thing moves in at 4 meters per second, what has to be their velocity that they move off with afterwards, if the masses are identical? So if this one is moving in at 4 meters per second, what has to be the velocity afterwards?
Half of the initial velocity.
Otherwise known as?
I don't know. I'm stupid.
2, right? Okay. So because of the fact that because I'm going to double my mass, the velocity has to become half to conserve momentum. So then when you look at the idea that because that kinetic energy is 1/2 mv squared, so whenever you make any changes to the velocity, that's a big change in terms of your kinetic energy. So we're dropping that velocity, so that means our kinetic energy isn't going to be conserved. So best case scenario, you have a perfectly elastic collision. They cannot stick together. They have to bounce because you have to end up with two different velocities. You can't have it this way because they're going to hit and they're going to stick together and they're going to end up with the same overall velocity. Got it? Good? Genres of entertainment.
Oh, have you watched Dexter?
Oh, I can see.
You will love Dexter. You need to go see
Yeah,
it.
rival.
Because he's a really smart dude. And kind of get into his mind and like, he knows more about other people than he knows about himself.
I know that.
Any fan?
Okay, so let's say that I want to find the center of mass of the meter stick, okay? So there's kind of a cool thing that you can do. So let's say that I put one finger over here at the 60 mark, and I put the other one way out here at the edge, okay? And I slowly begin to bring them together.
That finger's not.
And they meet under the center of mass. So I can do this, and even doesn't make any difference. If I start with this one like right here, doesn't make any difference. Wherever I start it, I'm going to end up under the center of mass.
Let me test this.
Just hold on. Now,
Oh, you shall use.
what would happen if I put like a 200-gram mass on one side? Is it still going to meet in the middle?
No,
No. Where's the center of mass going to be?
further this way.
Okay?
I guess at the 42 mark. Oh. Oh.
Okay.
Where are you at?
All right. I'm at 25. Okay? 45 inch mark. So if I put even more mass out here, what would happen? Center of mass would shift further and further and further. So you can do the same thing with an aircraft carrier, a submarine, a 777 jet. Okay? If you could do this, you could find the exact point where this thing is going to bounce.
When you get crushed,
Huh?
when you get crushed,
So, but there's an easier way to do this. And this formula that I have up on the board, and if you ever need it, I'll give you this formula on the test. It's fairly simple. So basically it's this. torque and center of mass is somewhat related, okay, but they're not. So like, if I take this meter stick, okay, use this, can't you?
Yeah.
And even if I take this and, no, keep it in the middle. So if I hang a more massive weight over here, and can you hand me that mass set, please? Because if I let go, this is going to fall. Thank you. Well done.
Wow. The next
So-
Vanna White.
He just brought it up.
Okay. So if you look at how
Yeah, seriously. How do you know that?
Wheel of Fortune.
Wheel of Fortune, Vanna White.
Yeah,
Vanna
see,
White.
everybody knows her name. How do you know that?
Jeopardy. Guy who does it.
Alex Trebek.
Dude.
I think I
He's a,
Dude,
he
I
is a
love
beast.
Jeopardy.
I'll take game show host for 500.
Wait, what if they did that? Like, weird guy who's been doing Jeopardy for 30 years.
No, just say no. Okay, so if I want to find the center of mass of this system, here's where this is different than torque. What two things do you need to calculate torque? Force and from where it begins to rotate. Center of mass is different because it's only based upon mass. It isn't based upon a force. So what that means is that the center of mass, whether I'm on Earth or if I'm in deep space, doesn't change. Center of mass is still in the exact same location. So this is why we use mass instead of weight. So if I want to find the center of mass of this system, here's what I would do. Typically, it doesn't make any difference where you start, but the easiest thing to do is to define one end as being 0. So like, for example, on today's assignment, you're going to find the center of mass of the Earth and Moon system, okay? You can choose to start in the middle. You can choose to let the Earth be 1 point. You can let the Moon be 1 point, okay? It doesn't make any difference, but it's easier if you make one of the distances be 0. So I'm going to start here. So if I were to find the center of mass of this, I'm going to make this 0. So I would find this distance from this edge to here. So I'd take that distance, I don't know, roughly 5 centimeters, and then I'd multiply that by 20 grams. Now, technically, because you're going to divide by the sum of the masses anyway, as long as the masses are all the same, they're going to cancel out of the equation anyway. So if you've got masses that are in grams, leave them in grams, because you're going to divide by grams anyway, and then you're going to get the center location of the mass. So it really doesn't make any difference. So if I were to do this, I'd start here at 0, and so then I'd have maybe like 5 centimeters times 20 grams, and then I'd come out here for the second one and have this second mass, which is 200 grams, times however far it is from this point. If I wanted to start here, cool. If I wanted to let this be 0, then I'd find this distance, multiply that by 200, and then I'd take this distance here and multiply that by 20 grams. It doesn't make any difference where you start. But if you want to, you can let one of these values be 0 because that's going to make it easier to work with. But here's what's important. All the distances have to be measured from wherever you start. So like if you're going to give the distance to this 200 gram mass, it isn't the distance between these points. It's the distance between where you start to measure from. Okay? So it is not this distance. If it's from here, it's to here. Now, you could let the center be your reference point. If you wanted to do this, cool. But then if you're going to do this, then you'd have to make this be like a negative value and make this be a positive value. That gets a little bit weird. So it's just easier if you say, hey, I'm just going to start at 1 point. I'm going to let that be 0. And I'm going to have everything go from there. Now, if you wanted to, you could have this one way out here on the edge. You could have this actually start at 0. So you could have one of your x values be 0. So if this is where you're going to start to measure from, and this is where that's located is at 0, fine, make it 0. It doesn't make any difference. You're still going to get the same answer. Okay?
What's in 3?
this, I'm just saying, it could go on and on and on. You could have 500 points, doesn't make any difference. This just goes on and on and on and on and on. Okay, that's just, but it doesn't make any difference, but you're always divided back by the sum of the masses. Okay. Okay.
So like when he was doing center mass, like he
Stop. In physics, what's the best way to get rid of a Kinker sword?
Oh, let it heal itself.
It's not doing that. What? I'm not pouring hydrogen peroxide in my mouth.
What help?
No way!
Just put it on a cotton swab and just dab it on.
That's what I heard. I've had the same like a week going away.
That is crazy.
Yeah.
I know they use it.
In the front?
No, it's like in my gum right here.
I would go check that out then, if you've had it for a little bit.
Yeah, talk to Kendra. If Kendra's going, ooh, you might want to go have that checked out.
If
Yeah.
you've had it for that long, and if it's that deep, are you sure it's a kinker sore?
I mean, I don't know.
Is it by your wisdom teeth? Like, is it like a...
No, it's literally like right. What would that have to do with right here?
Okay,
I'll look at it
so
later, Hunter.
here's how,
Literally inside my gum.
I'll look at it later, Hunter.
here's how you, okay. So let's say that here's your setup. This is as simple as it gets. So in this case, you take 0.2 meters times 1 kilogram, and then you take a half a kilogram. Now, here's where you have to watch. Don't use 0.2 meters for the distance of this. If you're going to assume that it pivots around this point, then you'd have to let this be 0.4 meters. Okay? Just don't use 0.2 because you got to go all the way back to the point where it's going to pivot about. And then your third point would be 0.6 meters, which is going to be that total distance times 5 kilograms. So, just looking at this, this is a 1 kilogram mass, this is a half kilogram mass, this is a 5 kilogram mass. So do you think the center of mass is going to be closer to the left or closer to the right? Yeah, because you got this big massive 5 kilogram mass out there. So you're going to do all of that and then divide it by the total of 6.5 kilograms. And if you go through the math, you get 0.523 meters. So what that means is on this system, center of mass is going to be somewhere in here. So if I were to put that fulcrum right here, this is where this thing would bounce. Now, what you don't have to worry about, but you have to in reality, is you don't have to worry about the mass of the rod itself, because you're usually told, oh, it's a thin rod of negligible mass. If this is like a 4x4 post, the post itself is going to have a center of mass, which would actually affect your calculations. So, but we don't have to worry about it on these, but I'm just saying, in reality, if you're doing this going, wow, I want to find the center of mass of, like, you know, a ship. The mass of the ship is going to be a contributing factor to this whole thing. So I'm just going to throw that out. All right, now, we're going to introduce this and do a lot more work on it tomorrow. What we haven't talked about is rotational kinetic energy, which is 1/2 I omega squared. So I is going to be measured in what?
Rotation.
I don't know.
Rhymes with moment of inertia.
Transition.
Moment of inertia.
Moment of inertia.
It's an moment of inertia.
Which is
And
going
it
to be,
rhymes with omen.
Oh, this is
What's moment of
rotational.
inertia?
yes. Generally MR squared, but what are the only two situations in when you can use MR squared?
Point mass.
Point mass or a
Fin hoop.
fin hoop.
Fin hoop.
Anything else you have to look up the moment of inertia? Omega is going to be measured in radians per second, and that's going to get radians squared. So if you look at this, so this I generally is moment of inertia. I generally has what units? What?
Newtons.
Not
Newtons.
Kilogram squared. Meter squared.
Kilogram meter squared.
Kilogram meter
I knew it was something.
Now, I'm going to multiply that by radians per second squared.
I knew it had seconds.
So the radians are dimensionless, so those.
So
So
it's
now slide in kilograms meters squared
second
over
squared, which is
second squared, which is the same thing as
Well, if you square root those,
No, hold on. What are
it's not Newton meters.
translational kinetic energy,
meters.
which is 1/2
There's so
mv
much going
squared,
on.
which is mass times.
You didn't square the radians.
they don't matter.
Doesn't matter. It's
Radians are.
It's not a thing.
Dimensionless dummy.
Then why are we
God.
because we can't.
Have you been in this class?
I've been gone a lot.
That is true.
Sorry.
So
When you're
here's the
drafted.
deal. No matter what.
You were here.
Now, if you look at this, here's what they have in common. If you have translational kinetic energy, that's 1/2 mv squared. If you have rotational, that's 1/2 I omega squared. This is moment of inertia, a resistance to a change in its,
Orbit.
well, or its angular velocity. This is mass, which is a resistance to change in linear velocity. This is how fast it's spinning. This is how fast it's moving. So they have the same type idea. You end up with the same units. So if I take yonder bicycle wheel, so right now, does it have a moment of inertia?
Why would it not?
Why is it
Yes, it
turning?
would.
Does this have a moment of
Yes.
inertia? Does it have mass?
Yeah.
Does it have a radius?
Yeah.
Yes. Does it have a
Yeah.
moment of inertia?
Yeah.
Yes. Does it have any rotational kinetic energy at this point?
No.
Does it have a
No.
velocity?
But as soon as I get it to
Oh.
Now it
spin,
does.
now it does. Now, to get it to spin, do I have to do work?
Yeah,
Yes.
you do work.
Yes.
Find a force over distance.
I exert a force through a distance. But here's what you have to be careful of. Okay? Be very careful about work calculations in kinetic energy, because you can't, as far as distance, it isn't the distance from the hub. The distance would be how far it rotates while I'm applying that force. That's what I use in my work calculations. But there's a simpler way to look at work calculations in terms of rotational energy. Because generally, in a broad idea, what does work equal? The change in, no, there's a broader idea.
Change in energy. Change it.
Changing energy.
Change in energy, right?
Okay.
Okay, so
Nope, I'm not
what's
quite.
the
Look at
initial kinetic energy of the wheel? Zero. So if I make it spin and I find my final kinetic energy, that's the work that's done. That's a much easier calculation than trying to figure out what distance and how much torque I apply through that distance. That's much more difficult to do. But if I can just find, oh, it starts at 0, or if I slow it down, I do work on it because of the fact that I'm changing that kinetic energy. Okay, and remember, power is change in energy over time, otherwise known as watts. Okay, so
You heard me.
okay.
I've been looking at that all day.
Do not overthink problem number 1. Number 1 is just a straight momentum problem. Timmy is in a boat, he's going to throw a rock. Okay? Everything is at rest, he's going to throw a rock. It's an old school momentum problem. Now, let's talk about problem number 2.
What? I just looked up all of a sudden. We can't pause it. I will look at it in 1 second. How much does it hurt?
Bad.
Did you try one of those like zinc
Be a
things?
doctor. Scale of 1 to 10.
I'm talking here and now.
Let's go.
That's a funny balloon.
This is a weird looking one.
I'm talking here.
What are you doing?
Let's go.
I could have had this Tinker Called fixed if you would have just allowed me to. Get the yellow one. Or orange.
Why does he have so many balloons?
Let's go with this.
Or the red one.
Apparently so. Okay, I need to take this.
Did you see that tweet that was like that?
Okay, so I've got a balloon.
You've got a balloon.
When I let go of it, what's going to happen?
It's going to
It's gonna shoot out this way.
So
Point it that way.
is the momentum of the balloon going to change?
Yeah.
Heck yeah, because it's at rest, right? Because you're going to have escaping gas going this way. So when I let go of it,
Damn it, heads up.
Actually, you could have a
Negative
situation where the
velocity.
balloon never changes, huh? Or if you have the perfect gas or solid in it, and as it's going out, it's being propelled, and it's losing the same amount of mass to make up for the velocity.
This man speaks words of truth.
And make the same noises.
okay, we've got this idea, right? Force times time equals change in momentum. True? Now, up to this point, you're used to saying mass times the change in velocity, right? You're used to mass staying constant and the velocity changing. But if you look at what happens with the balloon, the mass is changing, right? Okay? Which is basically how a rocket engine works. So the V is going to be the velocity of the escaping gas. So if you have a balloon, okay, with that escaping gas, here's what you want to look at. It's still force times time, but now we're going to have a constant velocity multiplied by a change in mass. So what this is going to be is how much mass is ejected per second. So it might be like realistically like on the space shuttle launches or any big rocket at all, this might be like maybe 2,000 kilograms per second. This might be, 300, 400 meters per second. So with rockets, you're keeping the velocity the same, and you're changing, this is the rate at which your mass changes. So if you look at this on a unit, well, you have force times time, which is Newton seconds, right? Which is kilogram meters per second squared times seconds. Seconds cancel out, you get kilogram meters per second. Over here, you've got meters per second times kilograms, you end up with the exact same units. So with rockets, you keep the velocity constant, change the mass. If you're making a car move, you're keeping the mass constant, and you're changing the velocity. Okay? So when you get to question number 2 on this assignment, pay attention to this idea. So on number 3, you're compressing it. This is old school conservation of energy On number 4, you have a solid cylinder. Tangential force of about 12 newtons is applied for 10 seconds. You've got to go old school. Torque equals 2 things. I alpha, it equals force times radius. So you got to go old school with that one. Then you're going to end up with the rotational kinetic energy. On number 5, I'm telling you it's a perfectly elastic collision. You're going to find the velocity of the board and the target before and after. And then on number 6, what would happen if I made the more massive one and the least massive one switch places? Number 7, you're going to collide head on. They're going to move off together. So go old school momentum. Okay, so this is Kendra's wheelhouse. Okay.
On number 7, you said it was old school?
7 is old school momentum. And then 10 and 11 are center of mass calculations. And no, there's not a backside. So I'm done. You're on your own.